Welcome to Sequences and Series. My name is Miss Gina Talon, and I will be explaining this Part 1 introduction for you today. Okay, as we move on to the guided notes, an infinite sequence is a function whose domain is a set of positive integers, 1, 2, 3, dot, dot, dot. The function values a sub 1, a sub 2, a sub 3, dot, 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 a sub n, dot, 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 are the terms of the sequence. If the domain on the function consists of the first n positive integers only, the sequence is a finite sequence. So let's decipher what this is actually saying here. This right here is a sub 1, and it's read as a sub 1, and it represents the first term of the sequence. First term because of this 1 sitting right there. That's your first term. A sub 2 is read as a sub 2 and represents the second term of the sequence. Now what is it that's read as a sub 3? So this should be a with a little subscript 3, and it represents the third term of the sequence. A sub n is read as a sub n, which I suppose I should underline a sub 2 also, and represents the, and this is kind of weird, but it's the nth term of the sequence. So for instance, if it was a sub 10, then it would be the 10th term of the sequence. A sub 14 would be the 14th term of the sequence, and so on. Basically, a sequence is a list of, what are they? Terms separated by commas. Pretty simple. For example, list the first four terms in the sequence defined explicitly by a sub n equals 3n minus 2. So I'm going to start here. A sub n equals 3n minus 2, and I am going to substitute a 1 to find my first term. So 3 times 1 minus 2, that's 3 minus 2. So a sub 1 is equal to 1. Now if I want the second term in the sequence, then I take the original explicit definition of the sequence and I substitute n as 2. That gives me a sub 2 equals 3 times 2 minus 2. That's 6 minus 2. So my a sub 2 is equal to 4. And then I move on. I want the third term in the sequence, so I'm going to write the formula for the sequence, and I'm going to put a 3 in for n. A sub 3 equals 3 times 3 minus 2. That's 9 minus 2. So a sub 3 is equal to 7. A sub 4, you put a 4 in for n. That gives me 12 minus 2. So a sub 4 is equal to 10. Those are the first 4 terms in the sequence. Now I asked you to list them, so I would expect you to give me a list of these terms, like 1, 4, 7, 10. And that would be the answer to the problem that you could box. Okay? So we are listing the terms of the sequence. Sequence is a whole bunch of terms separated by commas. Alrighty, example 2. List the first 5 terms in the sequence defined explicitly by a sub n equals negative 1 to the n multiplied by 3n over 2n plus 1. So as you can see, I took the explicit definition of the sequence and I have repeatedly copied that over and over and over again so that we can substitute in straight from the formula each time. You can pause this video and do the same thing, although if you printed out the worksheet, you have the same thing that I have right in front of me, so you don't have to rewrite them. So I want a sub 1, which means I'm going to put a 1 in everywhere I see n. So notice this becomes a 1 right here, this n becomes a 1, and this n becomes a 1. So you simply substitute n equals 1 into the formula and evaluate the formula. So I'm looking at a sub 1 is going to equal negative 1 to the first is just negative 1, and I'm going to leave that in parentheses because I'm about to evaluate this fraction right here, and I'd like for this fraction to also be in parentheses so that I can show multiplication. So the numerator, 3 times 1 is just 3, And on the denominator, we're going to do a little bit in our heads here. 2 times 1 is 2, plus 1 is 3 again. So that just gives me a sub 1 equals negative 3 over 3, which of course we know is just negative 1. So we're good with our first term. Our second term is found by putting a 2 in for n. It is the nth term, so it is the second term. So negative 1 squared is going to just make positive 1. And then I'm going to have this fraction here that I'm going to wrap in parentheses to show multiplication. 3 times 2 on the numerator gives me 6. And on the denominator, 2 times 2 is 4, plus 1 is 5. So this gives me a sub 2 is 6 over 5. You may be thinking that you can reduce that. But if you change the 6 over 5 to 1 1/5, you're not actually reducing the fraction. What you are doing is changing the format of the fraction. You are switching from an improper form to a mixed form, but you haven't reduced. There's no common factors between the 6 and 5, so therefore a sub 2 equals 6 over 5 is reduced in improper form. Let's move on to a sub 3. So a sub 3 is negative 1 to the third, and of course you know that negative 1 times negative 1 times negative 1 is going to give you negative 1, multiplied by another fraction here. 3 times 3 on the numerator gives you 9. 2 times 3 is 6, plus 1 is 7. So my a sub 3 is going to equal negative 9 over 7. And moving on to a sub 4, I'm seeing a sub 4 is equal to negative 1 to the fourth. That's going to give me a positive 1. Multiplied again by this fraction. 3 times 4 on the top gives me 12. On the denominator, 2 times 4 is 8, plus 1 is 9. So a sub 4 is just 12 over 9. And if you'd like to reduce 12 over 9, both the 12 and the 9 divide by 3. So my a sub 4 could indeed be called, I don't like that a. A sub 4 could be called 4 over 3 if you want to. Okay. And now we're moving on to a sub 5. Negative 1 to the fifth is going to give me negative 1. And this fraction that we have here, 3 times 5 on my numerator is going to give me 15. 2 times 5 is 10, plus 1 is 11 on my denominator. So a sub 5 is equal to negative 15 over 11. Now it doesn't really matter if the negative sign is on the numerator near the 15, or if the negative sign is outside of the fraction to the left. But please don't make that negative sign go on the denominator, okay? Just leave it where it is right there. And I don't want any of those things popping up. So, all right, moving over here, I need to list the first 5 terms. So my first term, see, I would have a sub 1. Let me see here, get back here. I would have, this happens to me occasionally, but we'll make it work. All right. A sub 1, comma, a sub 2, comma, a sub 3, comma, a sub 4, comma, a sub 5, comma. This is my list of my first 5 terms. I'm looking at negative 1, 6 over 5, negative 9 over 7, 4 over 3, and then negative 15 over 11. And these are my first 5 terms. Very nice. Try never to let your box touch a piece of your answer. Alrighty, just clean this up, make that 15 look a little nicer. I want to go back and talk about this negative 1 to the n idea that we see inside this explicit rule that defines our sequence. What did that negative 1 to the n do? It's right up here. See where I'm talking about? Negative 1 to the n. When we evaluated negative 1 to the n with n is 1, we just got negative 1. I'm going to change colors here for a second. We just got negative 1. And then when we did negative 1 squared, that evaluated to positive 1. Negative 1 cubed evaluated to negative 1. Negative 1 to the fourth evaluated to positive 1. Negative 1 to the fifth evaluated to negative 1 again. So what is the purpose of this negative 1 to the n? Can you see what it's doing with my terms? I'm hoping that you're thinking to yourself that you're alternating signs. So negative 1 to the n definitely alternates. Nope, get out of here. LTER alternates signs starting with a positive or a negative. starting with negative. And that's going to be kind of important for you to know, okay? This is super important for you to play around with, because at some point we're going to be taking these lists, this sequence, and we're going to be trying to create the explicit definition algebraically. So we want to know if the signs are alternating, you know, negative, positive, negative, positive, negative, positive. I'm going to definitely have a negative 1 to the end someplace in my problem. Okay, moving on. Example 3. List the first 5 terms in the sequence defined explicitly by a sub n equals 4 plus negative 1 to the n plus 1. So first thing I'm going to do is find a sub 1, which means all I have to do is put a 1 in. And I'm going to blow this up a little bit so I can be nice and big. I'm going to put a 1 in here, which is going to put a 1 here. And then I'm going to evaluate a sub 1 is equal to 4 plus, now negative 1 to the 1 plus 1. Notice the whole exponent here is 1 plus 1. So this is my entire exponent, n plus 1. So this is going to become negative 1 squared. So I got to add the 1 plus the 1 to get my exponent before I apply that exponent to the base, which is negative 1. This is going to yield a sub 1 is equal to 4 plus, and negative 1 squared is just 1. So this gives me a sub 1 is equal to 5. Okay, let's move on to a sub 2. So I'm going to put a 2 anywhere I see an n. See that? N is 2 for my second term. So a sub 2 is equal to 4 plus negative 1. Now what is 2 plus 1? 3. So this is going to give me a sub 2 is equal to 4 plus, and negative 1 cubed is negative 1. 4 plus negative 1 is the same thing as 4 minus 1, if you will. I will leave that there, even though I don't really think we needed to write it. But that should give me a 3 for my a sub 2. Let's move on and do a sub 4. Nope, a sub 2. I want a sub 3. Sorry about that. So now I'm going to put a 3 in for my n. This will yield a sub 3 is equal to 4 plus negative 1 to the 4th. We see that? This is going to give me a 4. So my a sub 3, you probably already have this answer off the top of your head already, but this is just going to be a positive 1 right here. A sub 3 is equal to 5. Now it's time for a sub 4. So I'm going to put a 4 anywhere I see my n. This is going to be a sub 4 is equal to 4 plus negative 1 to the what? This is to the 5th. So a sub 4 will equal to 4, and this is going to be plus a negative 1, but it's just going to be, again, 4 minus 1. And what's 4 minus 1? Right back to what it was a few minutes ago. My a sub 4 is actually equal to 3 again. Let's move on to a sub what? A sub 5. So put a 5 in here. So this is going to be a sub 5 equals 4 plus negative 1 to the 6. Negative 1 to the 6 is just 1. And 4 plus 1 is 5. So a sub 5 is 5. Again. So I know you weren't capable of seeing all of these at once, but you are now. So let's see what our list looks like. My a sub 1 is 5. My a sub 2 is 3. My a sub 3 is 5. My a sub 4 is 3. My a sub 5 is 5. And it's going to continue to do this, and just like you're thinking, it's just going to alternate back and forth between 5 and 3. There's my answer box here. Very good. Okay. So again, we're going to have to be able to come up with some kind of a formula that represents the pattern of the sequence 5, 3, 5, 3, 5, 3, and so on. let's just take a peek like we did before and see if we can just break this apart slightly, see what we have. I think I'm going to switch to a smaller. There we go. Okay, so I had -1 to the n plus 1. Can you guys like think about this for a minute and tell me what you think this piece, I don't want to do that. I don't ever want to do that. Let's go back. Let's see what that piece right there is doing to each one of our terms. So the 4 is in each term. You can see that. I can underline that 4 every single time. You see that 4? That's a constant. That's just part of the original statement. Okay, so I'm going to bring those back off. And I'm going to talk about this -1 to the n plus 1. When we put a 1 into that n right here, it turned that exponent into a 2, which meant -1 squared turned into +1. And then when we put a 2 in, then 2 plus 1 gave us an exponent of 3, and that turns into a -1. And then again, +1, -1, +1. So that -1 to the n plus 1, let me switch back in here, -1, quantity to the n plus 1 is going to do kind of the same thing it did up here. We're going to alternate signs, but this time we're not alternating starting negative, we're alternating starting positive. So I'm going to write alternates signs starting positive. And again, this is going to be very important for you to make sure to remember this, because if I give you a sequence that jumps back and forth between two numbers, you're going to have to decide whether I'm starting with the bigger number first or the smaller number, so whether I want to actually add or subtract first, and so on. Plus, one more thing just to mention here, since I am alternating between 5 and 3 and 5 and 3 and 5 and 3 and 5 and 3, it does make sense that the 4 is involved in the problem, I hope, because whatever is smack in between the 5 and the 3 is going to be what you have to add or subtract something to in order to get that number. So 4 plus 1 gives you the 5, 4 minus 1 gives you the 3, 4 plus 1, 4 minus 1, 4 plus 1, 4 minus 1. And we'll do another one of those examples in a little while. But that would be one of the first things that I would hope anybody would do, is find the number in between 5 and 3, exactly, smack dab in the middle, and rewrite the 5 as 4 plus 1, and then rewrite the 3 as 4 minus 1. And then rewrite the 5 as 4 plus 1, and rewrite the 3 as 4 minus 1, 4 plus 1, 4 minus 1, and so on. And now you can see it's a little easier to create the formula for it. Alrighty. Moving on to example 4 then. List the first 5 terms in the sequence defined explicitly by a sub n equals that. Okay? Now somewhere in here, and I don't know where, let me see if I'll be able to do this. If I were to tap my finger here and paste, yes. Okay. I have a little something that helps us figure out what this means. And it looks like I need to bring it up quite a bit. I kind of forgot to copy this over again, so it's okay that it's here. Because what we're going to do is just move over a bit. And you know what? That looks like a bad idea, doesn't it? Because it looks like I missed. There we go. Okay. I'm going to come over to the side, way over to the side over here, and paste. And see if that allows me to keep that where it was. Very good. Okay, that's better, Gina. I talk to myself all the time. All right, so let's open this up. And let's come over here And just think about this right here. All right, so there's an n, and then there's an exclamation mark. This is read as, quote unquote, n factorial. That's what this is read as. And there's actually buttons on your calculator for factorials. So this is a real, honest to goodness factorial thing. N factorial is equal to n times n minus 1 times n minus 2 times n minus 3 dot 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 all the way down to 2 times 1, as long as n is a positive integer. This right here says n is a positive integer. So positive integers start at 1 and then 2, 3, 4, 5, and so on. So n factorial is equal to 1, which makes pretty good sense, only when n equals 0. You know what? I shouldn't have said that. That's kind of backwards a little bit. Not only when n equals 0, because when n equals 1, we also have n factorial is equal to 1. So this is just an extra piece of the definition of what factorial means, because a lot of people think 0 factorial would equal 0, when indeed, if your n is a 0, n factorial is equal to 1. So 0 factorial by definition is equal to 1. That's why it needs to be stated separately, because it really doesn't follow that format whatsoever. Okay, so I hope that works out with everybody. I'll give you the list over here of different factorials. So 0 factorial is equal to 1, and I wrote by definition. 1 factorial is 1. 2 factorial means 2 times 1, which is 2. 3 factorial means 3 times 2 times 1. So you start with your n, and then you take 1 away, and then you take 2 away, and you take 3 away, and you just keep going down where integer values. That gives you 6. I'm going to come over here to the left-hand side where this 8 factorial is. 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And what I did is I just grouped 2 of these things at a time. So 8 times 7 was 56, 6 times 5 was 30, 4 times 3 is 12, 2 times 1 is 2. And I just left it like that. Now, for some reason, I don't have my writing ability. And then 56 times 30 was 1,680, 12 times 2 is 24, and then I multiply those together and you get 40,320. And that's the same as 8 factorial. So factorials get really big really fast. So 4 factorial, I'm coming back over here to this list of my factorials. 4 factorial is 4 times 3 times 2 times 1. But didn't I just do 3 times 2 times 1? And got 6 up above, so this gives me 24. So 4 factorial is 24. 5 factorial is 5 times 4 times 3 times 2 times 1, which didn't I just do? 4 times 3 times 2 times 1? That was 4 factorial. So 5 times 24 should end up giving you 120. Okay. And moving on past there, where are we? 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. Looks like I left something out there. Which is 6 times 120, because didn't we just do 5 times 4 times 3 times 2 times 1? So that's 720. And now 7 factorial is going to be 7 times 720. So I hope everybody's okay with that. All right, that answers 5,040 or 5,040. Again, that's 7 times 6 times 5 times 4 times 3 times 2 times 1, dot, dot, dot. And if I wanted to list my factorials, they would start 1, comma, 1, comma, 2, 6, 24, 120, 720. I could even put 5040 in here, and I could go dot, 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 because the next one would be 8 factorial, which we just did over here, right? 8 factorial. So if you multiply 5,040 times 8, I'm pretty sure you can see that that would give you 40,320. So you know what factorials are. They're used a lot, like all over the place in statistics. So when you're doing permutations, combinations, things like that. Alrighty. Let's come back over here now and let's see about our example number 4 now that we have a little bit better understanding of what factorial means. So we're going to go for listing the 5 terms in this sequence. I want to put a 1 for my n. This gives me a sub 1 equals 1/2. To find a sub 2, I want to put a 2 in here. This gives me 2 factorial is 2, and 2 times 2 is 4, so this kind of works weird. I got the same answer as I had for a sub 1. A sub 3 says go ahead and put a 3 in for my factorials. So this is going to give me 3 factorial, which I hope you know is 6, right? Divided by 2 times 3, which is 6. And this gives me a sub 3 is equal to 1. I'm looking at a sub 4 now, so I'm going to put a 4 in. Okay, 4 factorial, again that's 4 times 3 times 2 times 1, or hopefully you have it, which is 24. You can also think of that as doing 6 here times 4. Okay, divided by 2 times 4 is 8. Stop. And so my a sub 4 is 3. And now I want a sub 5, so I'm looking at 5 factorial. Whoops. Divided by 2 times 5. 2 times 5 is 10. I can do that fast. 5 factorial, I think if memory serves me right, was 120. Right? If I do this times 5, I get 120. Yep. So then my a sub 5 is simply 12. And if I want to list these numbers in order, I have 1/2 as my first term. I have 1/2 as my second term. I have a 1 as my third term, a 3 is my fourth term, and a 12 is my fifth term. This particular sequence, finite sequence, because it ends, it doesn't go forever, so I have a finite number of terms. This would be a really hard sequence to turn around and try and write an explicit definition for. And the reason it would be tough is because I've taken all my answers and reduced them. But if I had the answers in this format, the 1/2, the 2/4, the 6 over 6, 24 over 8, 120 over 10, I really think that the denominators 2, 4, 6, 8, 10, you'd see those as even numbers, so 2n wouldn't be so hard for you. And if you look at 1, 2, 6, 24, 120, I don't think you'd find a really hard time figuring out that those are your factorials. So reducing kind of is misleading if you're trying to go backwards. All right, let's move on to example 5. So in example 5, I have list the first 5 terms in the sequence defined explicitly by a sub n equals -1 to the n multiplied by 5n over 2 to the n. So this -1 to the n, what I'd like to see you guys doing is marking up your paper a little bit. This is going to alternate signs starting what? Starting how? If you put a 1 in there, whoops, if you put a 1 in here as your exponent, come on. I guess my pen does not want to cooperate with me. Okay, I'll hit the back arrow. There you go, starting. If we put a 1 in here for your n, -1 to the first is negative. So this would be starting negative. So think about it. 5n right here, 5 times 1, 5 times 2, 5 times 3, 5 times 4. These are your multiples of 5. And then 2 to the n right here, these are your powers of 2. So you can look at each piece of your explicit definition for your sequence and you can have an idea where it's going to go. Alrighty, let's do these. A sub 1, put a 1 in for your n, and this I already did for you right here. So you see your 1 is going in here, and your 1 of course is being substituted in the n and substituted in the n. A sub 1 is equal to -1 multiplied by, and I'm going to leave that just like it is right here. Let me just see for a second. Okay, so this gives me 5 on the top, and then 2 to the first is just 2 on the bottom. I know that looks kind of weird, Let's make it look nice. How's that? And this is -1, so my a sub 1 is -5/2. My a sub 2 is what I'm going to get when I put a 2 in for my n value. So -1 squared gives me a +1. I don't have to write the plus sign. I just chose 2 for this example. 5 times 2 on my numerator gives me 10, and 2 squared on my denominator gives me 4. So my a sub 2 is 10 over 4, which reduces down to 5 over 2. My a sub 3 means put a 3 anywhere you see an n in the explicit definition. -1 to the third is -1. And see how we were right about this? See how this -1 starts, and then +1, and then -1, and it's going to be a pattern as we go through. So we were right way up here when we said we were going to alternate signs starting negative using this -1 to the n idea. So anyway, 5 times 3 is 15, and 2 to the third power is 8, so my a sub 3 gives me -15 over 8. I don't like that bar. There you go. A sub 4 means put a 4 in everywhere you see the n. So my a sub 4 is -1 to the fourth, which is again +1. I'm just going to write 1 this time. 5 times 4 on my numerator is 20. 2 to the fourth on the denominator is 16. So my a sub 4 is equal to 5 over 4. Everything going okay? And then now we're going to do our a sub 5. So I think I'll bring it over because it's easier for me to write. I'm going to here. So this is a sub 5 is equal to -1 to the fifth is -1. 5 times 5 is 25, and 2 to the fifth is 32. So this gives me an a sub 5 as -25 over 32. And by the way, I know 25 and 32 are not going to reduce because I have no number that divides into both those, 25 and 32. All right, I'm going to come back here. I know most of my work is done, but I have to finalize my answer accurately, which said list the first 5 terms. It didn't just say write them on your paper someplace. I need to write them as a list. So my first term is -5/2. My second term is +5/2. I think my screen wants me to go higher. -15 over 8 for my a sub 3, 5 over 4 for my a sub 4, and -25 over 32, and that is going to be my a sub 5. So I want to box this. Let's see if I can do something different. There we go. There we go. Boxed our answers kind of fast. So I know that the first 2 don't really look all that great. -5/2 and then 5/2. You're not kind of seeing your multiples of 5 and your powers of 2s. But that's because things are reducing. That's basically what happened. Okay, if you could have gone back and compared your 5/2 to your 10/4 to your 15/8 to your 20 over 16, 25 over 32, then you would see that pattern a little bit better. So let me just do something for you here. Let me just highlight this. If I highlight this 5 over 2, 10 over 4, 15 over 8, 20 over 16, 35 over 32, hopefully there you can see your multiples of 5 are on top and your powers of 2 are on the denominator. Okay, and again, what's highlighted in yellow is your alternating sign starting negative. Okay, moving on to example 6 now. List the first 5 terms in the sequence defined recursively by a sub 1 equals 18, a sub k plus 1 equals a sub k plus 5. So I want to talk about these subscripts here for a minute because I know they can seem a little confusing when you first get into them. Let's see, right above it, how can I talk this out? Let me see, I can start by getting rid of that first off. Okay. Whoops, let's stay there. So if I have a sub 1, my next term would be a sub 2, my next term would be a sub 3, and then so on until I got to, let's just call this, I'll leave that one blank, I'll leave that one blank, I'll leave that one blank, dot, 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 and so on. If this one were a sub, let's say a sub 12 or something, then isn't the one right before it a sub 11? So the one right before it, you'd have to take one away from the 12. So the term before a sub k is considered a sub k minus 1. that would end up being a sub 11, if indeed k were 12. The one after a sub 12 would be a sub 13, which means I have to take the 12 and add 1 to make 13. So in the representation in terms of k's, it would be a sub k plus 1. And if I felt like it, instead of a dot, 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 I could say a sub k plus, if I add another 1, it becomes a sub k plus 2, and so on. Likewise, over here, if I wanted to add 1 in here, it would be a sub k minus 2. I hope that makes good sense to everybody here. Alrighty, so basically this right here is a recursive statement, and it's a recursive statement because it builds on something previous. If I want to know what is a sub k plus 1, I have to know what is a sub k in order to find it. And a sub k compared to a sub k plus 1 is the term right to the left of it, or right before it. So in order to get the next term, you have to have the previous term. And that's why we have a recursive statement. Alrighty, so we'll talk about that one more time as we go through this whole thing. A sub k plus 1 equals a sub k plus 5, and I wrote that 5 times for you. I already know my a sub 1. Let's come down here and write a sub 1, a sub 2, a sub 3. I want 5 terms, a sub 4, and a sub 5. So I want 5 of them. I already know a sub 1 is given as 18. So that's something cool with recursive statements, is they got to give you something. So if they're giving you a sub 1 and that's all you have, then that's what you need to use in order to find something else. So I'm going to start by using my a sub 1 and adding 5 to it, which means that k equals 1 in this problem. And if k is equal to 1, then what I'm actually finding is a sub 2. Now you could have, instead of saying I'm going to use my a sub 1, you could say, okay, I have a sub 1, I need to find a sub 2. And if I want to find a sub 2, I want the 2 to be here, which means I need to add a 1 to 1 in order to make 2. That means my k value is a 1. All right, either way, k is a 1, which allows us to do this. This is going to be 18 plus 5. So my a sub 2 is 23. Let's go to a sub 3. If I want a sub 3, then isn't it true that my k value has to be a 2 in order to make that become 2 plus 1 is 3? This will be equal to a sub k, which is a sub 2, plus 5. A sub 2 is 23, so that's going to come right in here. I'm going to get a sub 3 is 23 plus 5, so my a sub 3 is 28. And now I want to find a sub 4. If I want a sub 4, that means that this whole quantity right here has to equal 4. And the only way that quantity will equal a 4 is if the k itself is a 3, right? So this will be a sub 3 plus 5, which I just found out, so that's going to come up over here. My a sub 4 is going to be 28 plus 5, making my a sub 4 equal to 33. Very nice. So now I have a sub 1, I have a sub 2, a sub 3, a sub 4. I want a sub 5. In order to find a sub 5, I have to let this k value equal 4. So this k value will equal 4 as well. This is a sub 4 plus 5, which is pretty nice because I just found a sub 4. Yikes. It's going to be this. It's going to come right here. And I'm going to get 33 plus 5. So my a sub 5 is 38. So my pattern, my a sub 3 was 28. I didn't write that down. 33, I didn't write that down. And 38, I didn't write that down. So, pretty good. Pretty easy to do. I'm going to box my answer. Not like that. I don't like that. Let's back out of that again for a minute. Ink to shape. It doesn't want me to. Shapes, sorry. I wonder if I can just. Very good. Okay. So there are our 5 answers. Notice, will you, that this particular pattern is pretty easy to pick out. 18, 23, 28, 33, 38. You can pretty much guess the next number is going to be 43, 48, 53, and so on. They keep going like that. But you can tell that these numbers are increasing by 5 each time. Well, look at the recursing pattern. This a sub k plus 1 equaling a sub k plus 5 says in order to find the next term, you take the previous term and add 5. So recursive definitions are really kind of neat. Although when I ask you to create an equation or a definition for a sequence, I won't be asking for recursive. We will be asking for explicit. And the terminology between recursive and explicit is kind of neat. With an explicit function, if I wanted a sub 50, I could just plug a 50 into the problem, and I could plug a 50 into my definition, and I can get my term for a sub 50. With this recursive definition, in order to find a sub 50, I need a sub 49. But in order to find 49, I needed 48, 47, 46, 45, 46, well, that was bad, 44, 43, 42, 41, and so on. So you have to have all of the previous terms in order to get the next one. And that's recursive, which I particularly would prefer to have an explicit function defined as opposed to a recursive one. Alrighty, so I hope that makes sense for you. You might want to rewind that and play that again for yourself. But the recursive pretty much always has the case stuff involved in it, where the explicit, when you define something explicitly, the n is sitting involved in it, because if I want the 12th term, I can put a 12 in and get it exactly by doing one thing. So explicit, you get exactly what you need real fast. And recursive just sounds like you're cursed. You got to do the whole work in order to get to the next term. All right, well, let's do another one anyway. So we are going to list the first 5 terms in the sequence defined recursively by a sub 1 equals 24, a sub k plus 1 equals 1/2 a sub k. So my first term is 24, no doubt about it. That's my a sub 1. And now I need a sub 2. So let's say, okay, I want a sub 2. In order for me to think about a sub 2, I would have to let k equal 1. And if k is equal to 1, I can do the rest of this problem. So let's put this 1 like this, which means I'm going to have to do 1/2 of a sub 1. I'm going to just write a sub 1 first. So a sub 2 is 1/2 of, and a sub 1 was given to me as 24. Half of 24 is 12. Now I want a sub 3. In order to get a sub 3, my k value would have to be a 2. So a sub 3 would be 1/2 a sub 2. A sub 3 would be 1/2 of, and here it is right here. See, I'm going to use it. 12. Half of 12 is 6. And I will use that 6 in the next one. So I want a sub 4, and that's going to be 1/2 of a sub 3. So my a sub 4 is 1/2 of 6. Notice how I'm showing each step individual, so it's nice and clear. I don't think anybody can get too lost on this as we're doing this. My 6 is coming in here. All right, now I want a sub 5. So this is 1/2 of a sub 4. A sub 5 is 1/2 of 3. And a sub 5 is equal to 3/2. So now we're going to list them. So my first term was 24. My second term is 12, 6, 3, 3/2. And can you just guess what the next term would be without doing any work? I'm hoping you'd come up with 3/4, 3/8, 3/16, 3/32. And what's happening here? Simply with that, you're taking another half, you take another half, you take another half, you take another half, and as you continue to take halves, your denominators double. Okay, they multiply by 2. This should make sense. Okay, example 8, and I think this is the last recursive example we have, yes. So get a little more complicated on this one. My a sub 1 is equal to 5. And I have a sub 2 is 11. So all I need are a sub 3, a sub 4, and a sub 5. Let's see. I'm going to have a 5. I'm going to have an 11. I need that number, and that number, and that number. And then I'm going to be done. Well, let's just see here. So I have a sub k, I have a k plus 1, and I have a k plus 2. So this is how they would fall. A sub k plus 1, a sub k plus 2, and so on. So the a sub k would be the one you know first. The a sub k plus 1 would be the next one. K plus 2, a sub k plus 2 would be the third one. Because I one after that. So let's see how we're going to do this. Let's say if I wanted to find a sub 3. Let's just try it. A sub 3. Now if I want to find a sub 3, what k value do I need? I would need a k value of 1. Because only 1 plus 2 makes 3. So if my k value is a 1, this means that the k value here is a 1. All right. It also means that the k value here is a 1. So this would be a sub 2. So a sub 3 is equal to 3 times 5, because 5 was my a sub 1, minus 2 times 11, because my a sub 2 is 11. All right, let's do this simplification. This gives me 15 minus 22. What's 15 minus 22? I'm hoping everybody has negative 7 in their mind as my a sub 3. Now I want to find a sub 4. And in order to find a sub 4, now my k value would have to be a 2. And that doesn't really look all that nice. So if my k value is a 2, then a 2 has got to go in for k throughout everything here. So this is going to give me 3a sub 2 minus 2a sub, and what's 2 plus 1? 3. So a sub 4 equals 3 times minus 2 times. Let's see, my a sub 2 is 11, and my a sub 3 we found out was negative 7. So I have a sub 4. See how this is recursive because I have to use this number here into the next term? That's recursive. 33 minus 2 times 17 is going to turn into a plus 14, and my a sub 4 in this case is going to turn into 47. It's a bigger number than I thought. Did not anticipate that. Let's move on to a sub what? 5. If I want a sub 5, then my k value has to be a 3. So I'm going to put a 3 everywhere I see k. This is 3a sub 3 minus 2a sub 3 plus 1 make 4. So my a sub 5 is 3 times this minus 2 times that. A sub 3 is negative 7, and a sub 4 is 47. So a sub 5 is negative 21 minus 94, which gives me negative 115. Negative 115. I would have never guessed that. This is a very strange recursive definition because your next term doesn't just rely on the one before it, but it relies on the 2 before it. So it gets to be a little kind of crazy, huh? All right, let's box this answer. Good to go. I hope if anybody has any questions, you can bring them up in class. All right, so here we go. We are now going to write an expression. I wish this would play nice with me for a little while. We're going to write an expression for the nth term, for the apparent nth term, okay, of this sequence. So we're going to do what we can do to try and figure this out. Alrighty. Well, this one's kind of an easy one to do. I'm looking at this and I'm thinking 2, 8, 14, 20, 26, and something in my mind tells me that something is happening here. My numbers seem to be progressing at a constant rate, and you have to go from 2 to 8. That means add 6. You go 8 to 14 by adding 6, 14 to 20 by adding 6, 20 to 26 by adding 6. So if all I'm doing here is plus 6, plus 6, plus 6, kind of reminds me of that thing that did plus 5, but I don't want a recursive statement. I want an expression for the nth term. So I'm looking for a sub n equals, and I definitely want an explicit definition. Okay? Give me an explicit definition. So if I have a sub 1 is 2, I have a sub 2 is 8, I have a sub 3 is 14, I have a sub 4, a sub 5, 20, 26. I know that this 6 has something to do with the problem. Now how can I write, just try something. I mean, this is guess and check really at this point if this is your first time doing this. So if I want to write the number 2, how would I do that using the number 6? If I wanted to write the number 8 and the number 14 and so on, how do you think I could write an expression with an n involved in it so that when I plug a 1 in for n, the answer is 2. If I plug a 2 in for n, the answer is 8. If I plug a 3 in for n, the answer is 14. And so on. If I plug a 4 in for n, I get 24. So I'm going to look at this. Let me see, this 2 right here is just 6 minus 4, isn't it? That makes 2. And then this 8 right here, if I did 2 times 6 and then minus 4, that'll give me 12 minus 4. That's 8. Let's test that and see if maybe putting a 3 in here, 3 times 6 minus 4, 18 minus 4 is 14. That does work, doesn't it? Okay. So the thing that's changing here is the number that comes first, but that's interchangeable, isn't it? That could have been 6 times 2 minus 4. This could be 6 times 3 minus 4. And the next one could be 6 times 4 minus 4. Let's see, does it work for 6 times 5 minus 4? 6 times 5 is 30, minus 4 is 26. So yeah, it does. Okay, so another thing you can think of is that, you know, if you just added 4 to each of these terms, if you just said 2 plus 4 is 6, 8 plus 4 is 12, 4 plus 4 is 18, 20 plus 4 is 24, 26 plus 4 is 28. These are definitely multiples of 6 right here. That is so bad that I said 28. Let's go for 30. These are definitely multiples of 6 right there. So we are dealing with multiples of 6, but then we're subtracting 4 off from every one of those multiples to look at the pattern in our sequence. So this formula would be a sub n equals 6n minus 4. Now when you give this as an answer, you have to explain what it was you were thinking about. And the work that I have down here explains it. However, a lot of you are going to be doing this work right in your head, and you're going to be coming up with like little things you do off to the side to check and see if it works, and it's going to work. So your justification for me when you do something like that, and most of the work is in your head, is you have to prove to me, you have to prove to me, let me move over here so I'm not putting my palm on the right spot. You have to prove to me that a sub 1 would be 6 times 1 minus 4, which would equal 2. Put a check mark. You have to prove to me that a sub 2 would be 6 times 2 minus 4. Okay, 12 minus 4 is 8. Put a check mark. You have to prove to me that each one of these things checks. So this is literally a guess and check problem, because I haven't shown you how to do this any other way yet, which will be in the next video, by the way. There is a mathematical way when you notice that a pattern is increasing by 6 each time to come up with the formula, or if the pattern is increasing or decreasing by some other number, I will give you an algorithm to get that thing done. So 18 minus 4 is 14, 24 minus 4 is 20, and yes, I need to put a 5 in here, not a 4. 6 times 5 is 30, minus 4 is 26. So all of these work. So I would need this work from you, okay? If your thought process is in your head and you can't explain it to me well enough, then you're going to have to show me the guess. Here's your guess, and here's your check, okay? Alrighty, let's move on to the next one. Write an expression for the apparent nth term of this sequence. 1/3, -1/5, +1/7, -1/9, +1/11. I notice something is happening here. I notice that my signs are alternating, starting what? Positive. Okay, so when my signs start positive, it must mean that this is involved in the problem someplace. -1 to the n plus 1. If you look back further, we had that highlighted in yellow somewhere on the page. Okay, and if you look at the denominator, well, let's look at the numerator. It's constant 1, isn't it? But if you look at the denominator, what are these? Aren't these your odd numbers? Odds starting at 3. So how do you write odds starting at 3? That's a good question. 3, 5, 7, 9, 11. Okay, I pretty much have my a sub n equals -1 to the n plus 1 multiplied by a fraction with a 1 that's constant on top. But how am I going to make a 1 show up as a 3 down here? How am I going to make an input of a 2 show up as a 5? How do I get 3, 5, 7, 9, 11 as a pattern if I'm just looking at my denominator? Okay, can you tell they're going up by 2 every time? They're going up by 2, up by 2, up by 2, up by 2. Okay, so these are your multiples of 2, but something's happening to them. So your first multiple of 2 is a 2, isn't it? Isn't your first multiple of a multiple of 2 would be 2, 4, 6, 8, 10, 12. And these are 3, 5, 7, 9. So this would be like 2n. So if I wanted a 3, I would do 2n plus 1. If I wanted a 5, I'd do a 2n plus, sorry here, let me get my thoughts right before I start talking again. Okay, so if I wanted 5 for my second term, 2 times 2 is 4 plus 1 is 5. All right, so anyway, down here this becomes 2n plus 1. Because this number 3 is 2 times 1 plus 1. And this 5 is 2 times 2 plus 1. And this 7 is 2 times 3 plus 1. And this 9 is 2 times 4 plus 1. And this 10, yep, is 2 times 5 plus 1. So this would be the answer that I would have. Here's my shape. And let's box this answer. I don't like that box, so we're going to move it up slightly. And that's good enough. Okay? All right, do I have enough math on, come on, get away. Do I have enough math on my paper here to justify what it was I was doing? I indicated my numerators were constant. I indicated my denominator were the odd numbers starting out at 3. I indicated the signs were alternating, starting positive, so it's -1 to the n. And you can do that just like you know that right off the top of your head, okay? You can just tell me that, though, okay? So 2n was 2, 4, 6, 8, 10, 12. So 2n plus 1, if we add 1 to each one of these, we get 3, 5, 7, 9, 11, 13, so on. All right, I hope that makes good sense to you. Let's move on here. Example 11. So I have 5, 9, 5, 9, 5, and it's going to go 9 again, isn't it? I hope you know that, right? It's going to keep going. Alternating between 5 and 9 and 5 and 9 and 5 and 9. We did one of these before, but it alternated between, I think it was 5 and 3 and 5 and 3 and 5 and 3. And I told you then you had to find the number smack dab in the middle and then rewrite your sequence. So the number smack dab between 5 and 9 is 7. So I'm going to use the number 7 and I'm going to rewrite this sequence. So instead of 5, 9, 5, 9, 5, we're going to call this 7 minus 2, and then 7 plus 2, and then 7 minus 2, and then 7 plus 2, and then 7 minus 2, dot, dot, dot. And now things look a little bit easier to play with. So I'm looking at my 7 is constant. I'm looking at my a sub n is equal to 7. And now I have minus plus, minus plus, minus plus, and so on. They alternate. Signs alternating, starting with a negative. Signs alternating, starting negative. That's negative 1 to the n. See the signs alternating, starting positive was negative 1 to the n plus 1 up here. This is negative 1 to the n. And again, if you go back, you'll see highlighted in yellow that rule is there. So I'm going to put a plus sign because these are terms that I'm playing with, not multiplication this time. And I'm going to do negative 1 to the n. Then I'm going to throw the 2 in there. Doesn't it become 7 minus 2 plus 2 minus 2 plus 2 and so on? All right, so I'm going to box this. And you know what? That is enough information for me. I don't need you to do anything else. I need you to tell me that you've rewritten the pattern using the same number, just like I did, 7 minus 2, 7 plus 2, 7 minus 2, 7 plus 2, 7 minus 2, and then you can go ahead and you can write the equation for me. That's the biggest step, is recognizing that you need to rewrite the pattern. Alrighty. Okay, so let's move on to example 12. A little tougher on example 12, maybe not, I don't know, depends on you. Let's see where we have here. 1, comma, 5 over 2, comma, 25 over 6, 125 over 24, 625 over 120. I didn't even alternate any signs for you, so you got off easy on this one. So what do you think is going on with this? You notice anything? I noticed that I don't like that 1 written the way it is. I'll tell you what, I really don't. So I'm going to just kind of like scratch this out and write 1 over 1 so that all of my terms are fractions. So now I'm looking at 1, 5, 25, 125, 625. Do you notice anything about the numerators here? I hope you're saying they're all powers of 5. You go 5 to the 0, 5 to the 1, 5 to the 2, 5 to the 3, so on. Okay. And down here on the bottom, what's this? What are these? I'm hoping these are, you get the fact that these are factorials. Should I do a redundant feature right there? Factorials, factorial. Or does that just mean factorials? No. Okay. I'll erase it because I don't want it to confuse you. Okay. So powers of 5. When I do my powers of 5, I'm just going to write powers of 5 here. What do I normally start with? Don't I start with 5 to the first, and then 5 to the second, and 5 to the third, and then 5 to the fourth, and dot, dot, dot? So 5 to the first is 5. And then 25, and then 125, and then 625. But this isn't starting at 5. This is starting at 1. So don't I really want to back these up? Don't I want to kind of like divide all these by 5, so to speak, or take these powers down a little bit? I don't want to start with 5 to the first. This I need to be 5 to the 0. Then 5 to the first, and 5 to the second, and 5 to the third, and 5 to the fourth. Like, write those powers right on top of the numerator terms. Put them right in there. So my a sub n is coming a little more clear to me, that we're looking at 5 to the, and it won't be n, right? Because my first term is not 5 to the first. My first term is 5 to the 0. So I have to take 1 away from my exponent like that. So like, let's say if n were 3, then a sub 3 would be 5 to the 3 minus 1, which is 5 squared, right? And isn't this my third term? That's my a sub 3. Of course, now we have to play around with dividing as well, okay? So when you divide, you're going to have a little bit more to play with here. But factorials. What are your factorials when you list your factorials? Does anybody remember what they are? Okay, so 1 factorial, 2 factorial, 3 factorial, 4 factorial, and I'll actually do 5 factorial because it's sitting here. 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, and then 24, and then 120. So these are the factorials. I don't have to add or subtract anything from anything. All right, so this is just, this would end up being 3 factorial, which would give me a 6 here, right? And this would be 25 over 6 for my third term. So this is just n factorial. And I think there's enough work on the paper to justify what's going on. So we know we're talking factorials on the denominator. We know we're talking about powers of 5 on the numerator. Be careful though, because that power of 5 that you hit on that exponent for the top is not just 5 to the n. Okay, it's 5 to the n minus 1. Okay, so I think that makes pretty good sense. I think everybody, by showing 5 to the 0, by showing this work right here, that really helps me understand that. Alrighty, and that is going to be the end of what I'm talking about right there until I get on to some series. Okay, we are going to consider the infinite sequence, a sub 1, a sub 2, a sub 3, dot, 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 a sub n, dot, dot, dot. Infinite, of course, because of this dot, dot, dot going on here. Point number 1, the sum of all terms of an infinite sequence is called an infinite series and is denoted by, of course, the word sum means addition, right? So a sub 1 plus a sub 2 plus a sub 3 plus dot, dot, dot plus a sub n plus dot, dot, dot is equal to, and we have this process going on right here. We write, well, you see what we write, and we say the summation as I goes from 1 to infinity of a sub I. So I'm going to write that on the paper here. The summation, I'll put it in quotes, the summation as I goes from 1 to infinity of a sub I. That's what that says. So we can add an infinite number of terms up. You might be thinking, oh, how are you going to add an infinite number of things up if it never stops? Well, there is a way to do it in certain cases. All right, point 2, the sum of the first n terms of the sequence is called a finite series, or the nth partial sum of the sequence, and is denoted by a sub 1 plus a sub 2 plus a sub 3 plus dot, dot, dot plus a sub n equals the summation as I goes from 1 to n of a sub I. Notice there's no dot, 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 and therefore there's no infinity in this. So these are finite series because they come to an end. And we also refer to them as the nth partial sum. All right, so let's do a little bit of an example right here. So I have this symbol. It is read as the summation as I goes from 1 to 4 of 3 plus I squared. This little symbol right here is the Greek letter sigma. I is the index of summation, which, you know, I just have to tell you here, it's really just a dummy variable that helps keep track of which term you're on. It can be any letter, really, but when you look up the definition of summations and whatever, they definitely use an I, and it does stand for index of summation, so we will originally start with an I, although you could use a K or a P or a T or an R, any letter you feel comfortable using, even an N, which is kind of weird because we really like the N to go up on the top, but if N is not being used up on the top as your upper limit for your nth partial sum, then you really can use the n, again, because it's not defined for anything else, as your dummy variable that can represent the index of summation. All right, 1 is the lower limit of the summation, and 4 is the upper limit of summation. Also, that whole thing that I circled right here has meaning. So that summation as I goes from 1 to 4 of 3 plus I squared is equal to 3 plus 1 squared, 3 plus 2 squared, 3 plus 3 squared, 3 plus 4 squared, all added up with plus signs in the middle. I don't, you know what, I'm going to take these off because, yikes. I don't want you to think that that was a subtraction symbol. So I just take that off. All right, so we simplify this down. 3 plus 1 is 4. 3 plus 4, let's just do this. I know you can do this right in your head just like I can, but it helps to show all this work. So when you square 1, you get 1. You square 2, you get 4. You square 3, you get 9. You square 4, you get 16. And then you sum those up and you add your terms together and you get 42. And that's the end of that summation question. So this is actually called a series because a series is the summation of a sequence. Okay? A series is a summation of a sequence. The sum of all the terms of a sequence is called a series. The sum of all the terms of a sequence is called a series. Regardless of how many terms are there, whether there's a finite number of terms or an infinite number of terms, it really doesn't matter. You still, a series is the summation of a sequence. So it's kind of weird. You can't really have a series without having a sequence first, right? Example 13. Find the third partial sum of the summation as I goes from 1 to infinity of 6 divided by 10 to the I. I know you're probably thinking, what? How am I going to find that? The third partial sum just says that, yeah, we know this goes to infinity, but only add up the first 3 terms because it is the third partial sum. See up here it said the nth partial sum. The nth partial sum means you have n terms. So you only go up. In this case, you'd stop right here at the third term. Okay? So let's do this. We have the summation as I goes from 1 to 3 of 6 over 10 to the I. And you don't have to rewrite this like that. I just did that for some godforsaken reason, but I did it. So this gives me 6 over 10 to the first plus 6 over 10 to the second plus 6 over 10 to the third. See how my I is being substituted in now as I move on to the next term to the next term. It's kind of like the n previously. So this gives me 6 over 10. This gives me 6 over 10 squared is 100. And 10 cubed is 1,000. So that doesn't look like a 0 right there. I'm going to make it look more like a 0. Very good. I'm going to change to decimals because it looks nicer. And 6 thousandths is 0.006. And if I add these up, 0.6, 0.06, 0.006, I get 0.666. Maybe not the best question to have started with, but that is the answer to that question for the third partial sum. Pretty simple. Find the infinite series represented by the summation as I goes from 1 to infinity of 3 over 10 to the I. I want an infinite series. So first I got to look at it and see what it means, okay? So I'm looking at the summation as I goes from 1 to infinity of 3 over 10 to the I. This is 3 over, I'm going to start at 1, that's my lower limit, 10 to the first, plus 3 over 10 to the second, plus 3 over 10 to the third, plus 3 over 10 to the fourth, plus, and this just keeps going and going and going infinitely. So let's see what that gives us. 3 over 10 plus 3 over 100. This looks familiar. 3 over 1,000. It doesn't look like 1,000. And then 10 to the fourth, what would that be? 10,000? And I'm once again going to change these to decimals. This gives me 0.3 plus 0.03 plus 0.3 over 1,000. This is my tenths, my hundredths, and my thousandths. And now 10,000. And then so on. So if I go to add these up, 0.3, 0.03, 0.003, 0.0003. And wouldn't this, I mean, I can stop right there and say go ahead and add, but this is continuing down here like this. So, I mean, I can tell you right now the next one would be 0.0003 and then 0.000003 and so on. And it just keeps going and going and going. The answer to this is 0.33333333333333 dot dot dot, right? Doesn't it repeat? Or 0.3 with a bar over it. So 0.3 with a bar over it, you should recognize that as being the fraction 1/3. Okay? Now, if the previous example had gone to infinity, then it would be 0.666666666 and so on repeated. So you could have called that 2/3. But if it ends and it doesn't repeat, then you do not make it into the fraction 2/3. So this one up here stays where it is, and this one is just 1/3. All right, another little simple problem. Find the summation denoted by the summation as k goes from 3 to 5 of 2k squared plus 4. Careful, this summation starts at 3. So I'm going to write this over here, the summation as k goes from 3 to 5 of the quantity 2k squared plus 4. So this is going to allow me to start. Here's my first term. I think I'll put it in brackets this time just to be a little different. I'm going to put a 3 in. And after I put the 3 in, I'm going to do the same thing again, but I'm going to put a 4 into my dummy variable. And then I'm going to put a 5. And you just continue to substitute until you hit that upper limit. So should I keep going here? No, because 5 was my upper limit right here. So I have to stop here. This is where I start. And that's where I stop. So let's see what we have here. I could go slow for you, or I could go kind of fast for you. Let me see. 3 squared is 9, times 2 is 18. So this is 18 plus 4, which is 22. Plus 4 squared is 16, times 2 is 32, plus 4 is 36. Plus 5 squared is 25, times 2 is 50, plus 4 is 54. And this whole answer gives me 112. You know, I don't want to write my answer there. I don't like doing that. And I'm done. So if you're only doing a summation from 3 to 5, then you only have to substitute in the numbers 3, 4, and 5. And you substitute in integer values. Those are your inputs, which is why the definition of a sequence gave you that the domain were positive integers. Those are your inputs. Domain. Question 16, I think this is my last example. Give me the summation as r goes from 1 to 4 of r squared minus 6r plus 2. So this is indeed a series because we have to add up all of our terms. So I'm going to say, I'm going to do a big bracket. Something squared minus 6 times something plus 2, close my bracket. Do it again. Something squared minus 6 times something plus 2, close my bracket. How many times do I need this? How many times do I need to write this same situation over again? So I'm going to use r equals 1, I'm going to use r equals 2, I'm going to use r equals 3, I'm going to use r equals 4, and then I'm going to stop, right? So I'm going to put this in here one more time here. And I'm going to substitute a 1 in my first bracket, a 2 in my second bracket, a 3 in my third bracket, and a 4 in my fourth bracket. Okay? And we're going to evaluate this. This gives me something 1 minus 6 plus 2, which is negative 3, plus, this gives me 4 minus 12 plus 2, which is negative 6. So you can put a plus here if you want. Doesn't really matter. Plus, and I'm looking at here 9 minus 18 plus 2. This gives me negative 7 plus, and another bracket here. I'm looking at 16 minus 24 plus 2, which is negative 6. I put all these things together, and that gives me negative 22. And we are done. So you should have a really good idea as to what a sequence is. Just understanding what a sequence is, how to write out what a sequence is, given both an explicit and recursive definition. So going back here, we have our infinite sequence, our finite sequence. We should know how to read them accurately. We should know how to write out our work so that it's clear where the numbers are coming from. This is how we justify. This is justifying our work here. All right, -1 to the n, alternate signs starting negative, and so on. -1 to the n plus 1, alternate signs starting positive. And we came over here, we learned about our factorial, which you may or may not have ever seen before. I know that this is on an ACT and an SAT, so it's stuff that's there. Definitely big in statistics, probabilities. Okay. Explicit functions, recursive functions. I say functions, but aren't sequences functions, so I can interchangeably use the word function if I want. All right, this was kind of an easy one. This is turning around and actually writing the expression for a sub n, which is harder than just taking an a sub n equals and figuring out what the terms are. That's kind of simple. Going backwards is tough. Okay, but put your little notes down on your paper. Tell me what it is you're recognizing. And then the idea of summations, whether you're making a summation for that represents a finite or an infinite sequence. Okay, and in our next section we'll have formulas that help us do a lot of this stuff and makes things a little bit easier, but this is just an intro. All right, I have one more thing I need to say to everybody that is going to get done in, let's pick a different color. No, not that one. Let's pick big bright blue, and let's say, tell it out, people.